Nowadays, everyone has a power bank. But, have you ever wondered, how does it work? In this video, we will explore the circuitry that makes the battery work as a power bank or portable charger. This is the insides of the power bank. This is a lithium-ion battery. It has a nominal voltage of 3.7 volts, and the capacity of one cell is 5000 mAh at 3.7 volts. There are two of these batteries connected in parallel to increase the capacity to 10,000 mAh at 3.7 volts. This is the motherboard, and this is the PCB. It is used to support and connect components. This IC, DW01, is a lithium-ion or polymer battery protection IC. It is designed to protect a lithium-ion or polymer battery from damage or degrading the lifetime due to overcharge, overdischarge, and overcurrent. These are the two MOSFETs that function as a switch, connecting and disconnecting the battery as required. This IC, IP5306, is a charging-discharging, mobile power SoC. It is used to control the buck converter while charging the battery. Also, it controls the boost converter while discharging the battery. It also indicates the amount of charge in the battery with the help of LEDs. At last, we have two voltage dividers for biasing the D+ and D- pins of the device. Some devices will not start charging if they don't detect voltage at the D+ and D- pins. Also, there is this transistor to isolate the data pins from the supply pins, because some devices will try to communicate to the charger from these pins, and this will create fluctuations during charging. Now, let's see the working of ICs. This IC controls these two MOSFETs. One protects from overcharging, other protects from overdischarging. While charging, when the voltage of the battery cell exceeds the overcharge protection voltage for more than the overcharge delay time, charging is stopped by turning off the MOSFET OC. The overcharge condition is released when the voltage of the battery cell becomes lower than the overcharge release voltage through self-discharge or through a load. During charging, the flow of current is in this direction, that is, into the battery. As the MOSFET turns off and the internal diode is reverse biased, any flow of current in this direction is stopped. But, for discharging, the flow of current is in this direction. The MOSFET OD is on, and the internal diode of the MOSFET OC is forward biased. This allows the battery to be discharged to below overcharge release voltage, thus turning on the MOSFET OC. Now, if the voltage of the battery goes below the overdischarge protection voltage for more than the overdischarge delay time, discharging is stopped by turning off the MOSFET OD. The discharging is released when the voltage of the battery cell becomes higher than the overdischarge release voltage through charging. During discharging, the flow of current is in this direction, that is, from the battery. As the MOSFET turns off, and the internal diode is reverse biased, any flow of current in this direction is stopped. But, for charging, the flow of current is in this direction, and the MOSFET OC is on, and the internal diode of the MOSFET OD is forward biased. This allows the battery to be charged above the overdischarge release voltage, and turns on the MOSFET OD. Also, this IC can detect the charger. Once it detects the voltage between the current sense pin and ground pin, it turns on the MOSFET for charging. This current sense pin is used to measure the current from the battery at all times. If the voltage of the CS pin exceeds the overcurrent protection voltage, beyond the overcurrent delay time, the overcurrent protection circuit operates, and discharging is stopped by turning off the MOSFET OD. During discharging, the flow of current is in this direction, that is, from the battery. As the MOSFET turns off, and the internal diode is reverse biased, any flow of current in this direction is stopped. The overcurrent condition returns to the normal mode when the load is removed. This is how the IC, DW01, protects the battery from damage and degradation. Now, this is the main IC of this circuit. This controls the charging-discharging process, also monitors the battery in the circuit. This is the key pin. The voltage changes at the pin, due to button presses, are recorded and then processed to follow the instruction connected to the action. A single short press will indicate the battery charge with the help of these LEDs. There are 4 of them, each indicates a 25% charge of the battery. To calculate the charge of the battery, the voltage at the BAT pin is measured. These LEDs are connected such that each LED can be controlled individually. Hence, they are operated at high frequency to show continuous light. The charging of the battery is through a micro USB port rated at 5 volts. This is the graph of the charge cycle of a lithium-ion battery. The charging of a battery is to be done at a maximum of 4.2 volts. Hence we need to lower the voltage, so we use a buck converter. A buck converter is a circuit used to lower the voltage at the output than the input. A buck converter requires a switch, an inductor, a capacitor, and a diode, all arranged in this manner. Here, the battery itself is the capacitor and the load. And another switch is used instead of the diode. These two switches are inside the IC and are controlled internally. The working of the buck converter is explained in one of our previous videos. And while discharging, we need 5 volts at the output USB ports. Hence, we need to boost the voltage, so we use a boost converter. A boost converter is a circuit used to increase the voltage at the output than the input. Similar to the buck converter, a boost converter also requires a switch, an inductor, a capacitor, and a diode, but all arranged in a different manner. Also, the diode is replaced by a switch. The working of the boost converter is explained in this video. This is how the charging and discharging of the battery is controlled by this IC. As both of them uses the same components, thus we can either charge or discharge the battery, not both. This IC also protects from input over voltage, overcharge, overdischarge, overcurrent discharge, and short circuits. It also monitors the temperature of the IC. On the output side, we have two configurations for the USB connector. In the first one, the D+ and D- pin are directly connected. This indicates that the port is capable of supplying 1 amp of current at 5 volts. And the second one has a voltage divider to bias the D+ and D- pins to a fixed voltage, which will allow certain smartphones to draw 2 amps of current at 5 volts through this port. Now you know how a power bank works. Thank you for watching.